We look once more at the process of water rising in a thin tube up to a certain height, and then the gas expanding, forcing water out in order to do work. Assuming initial temperature 300 Kelvin and high temperature of 1200 Kelvin, and of course this is a lot higher than anything we're able to do in the lab with plastic bottles, we could get a graph which, drawn to scale, looks like this. Okay? We see that the pressure is approximately doubling here. And let's assume that the pressure does double, so that the pressure goes from 1 atmosphere to 2 atmospheres. That means we're going to be raising water about 30 feet, about 10 meters. And that's going to require us to double the temperature. In order to double the pressure, constant volume, we've got to double the temperature. Okay, and doubling the temperature will go from 300 to 600 Kelvin. So up here, when we get up to maximum height, the volume has doubled. Volume hasn't doubled. I'm looking at the wrong thing here. That didn't make any sense. Don't like the way I've got that arrow there. But anyhow, the water rises in the thin tube. The pressure doubles. As we can see just from the scale of the graph, that's a good estimate of what the pressure does. So we determine that the temperature goes up to double its original, which would be 600 Kelvin, not indicated on the figure. If we then allow the temperature to go from the doubled 600 Kelvin up to 1200 Kelvin, our second stage of the cycle will look like this, where the volume is going to double. We see that the volume goes from approximately here to approximately here. The volume looks like it's approximately doubling. And of course we're going to end up at 4 times the initial temperature, because to double the volume now at constant pressure we have to double the temperature. Okay, so first place, if this is drawn to scale where the pressure is doubling and then the volume's doubling, we've got to have twice the original temperature and then 4 times the original temperature. If the initial temperature is 300 Kelvin, round room temperature, then temperature here will be 600, temperature here will be 1200. Now let's contrast that with what happens in the system that we used in lab here, where the pressure certainly didn't double. It went from 100 kilopascals up to maybe 110 kilopascals. With the temperatures we had, we saw that the maximum work was done somewhere around that 110 kilopascal level. And then what happened? The volume expanded. The volume expanded just a few percent, okay? Maybe 10 or 15%. A very small change in volume. Well, in that case, the graph looks a lot like this. It doesn't, pressure doesn't double, volume doesn't double. Pressure just goes up a little, volume goes up just a little. Let's zoom in on it. We see the cycle there. That's as close as we can get. This is starting at a temperature of 300 Kelvin, going up to final temperature of 350 Kelvin, and a height of 0.9 meters. Now actually we did a little better than that. We went up over 350 Kelvin with some of our experiments. But to get the height of 0.9 meters, we have to increase the temperature to around 330 Kelvin, which only leaves us 20 Kelvin to increase along our constant volume, our constant pressure part of the curve. Let's see what the details look like. Now, without going into all the detail, if we have a final high temperature 1200 Kelvin, we can get this picture. For final temperature 350 Kelvin, assuming in both cases we start at around 300 Kelvin, the picture looks like this. Turns out that in this case we can increase the pressure by about 10%, the volume by about 5%. And you can work out the numbers on that. If we increase the pressure by 10%, that's going to get us up to 330. Actually, the volume goes up by more like 7%, but we're not going to worry about the precise figures here. There's a concept that we want to get. And the precise figures aren't that difficult to come by. Okay, so this means that if we do the complete cycle here, and the cycles have a similar shape, assuming cycles have a similar shape, and that's not necessarily a real accurate assumption, but still, the concept is what we're after here. It looks like this thing is maybe 10 times as high and 20 times as wide as this one. Now, if it's 10 times as high and 20 times as wide, it's got 200 times the area, or about, and that means that we perform about 200 times the work with this cycle than we do with this cycle. Now, 1200 is pretty high. If we use a good high temperature like this, in other words, we can get a lot more work out of the system. That shouldn't be any big surprise. The thing that might be surprising, though, is, yeah, this is a lot higher than this. From room temperature, here we're only going up by 50 Celsius. Here we're going up by 900 Celsius. We're going up by 18 times as much here as here. But going up by 18 times as much, getting 200 times the work, that's a pretty good deal. For 18 times the temperature rise, we get 200 times the work. And those numbers might not be completely accurate. It might be more like 100 times the work or 150. But it's still a lot more than the 18-fold increase in temperature change, okay? So 18 times the delta T, which means 18 times the thermal energy. Okay, that's what's important. We use 18 times the thermal energy to get 100 or 200 times the work. That is a real good deal, okay? This means that it's to our advantage to use the highest temperature we can in an engine of this nature. And if we have just a very low temperature differential, we're not likely to get very high efficiency. Now, in tapping the energy of temperature gradients in the ocean, we have a fairly low temperature differential, only 20, 30 degrees Celsius at the very most. Is that a good deal? Well, that's going to be a curve that looks like this more than this. That's not a good deal unless our delta Q comes very cheaply. And if you're tapping temperature gradients in the ocean, it's just a matter of pumping cold water and hot water into a system. Get the cold water from a greater depth, warm water from a lesser depth, and your delta Q really does come very cheaply there. If delta Q is expensive, then you want to use the biggest delta T you can and maybe use some different cycle. But there are limits on how efficient you can be depending on your temperature differential.